So, here's something worth thinking about as you settle in tonight. You are electric, not as a figure of speech. Right now, inside you, tiny pulses of electricity are moving. They run along your nerves. They tell your heart when to beat. Every thought you are having, this one included, is a small storm of electrical signals crossing the wet dark of your brain. You are, in the most literal way, a thing made partly of electricity. And you have never once felt it happen. There is more of it around you than that. The blanket, when you pull it back on a dry night, sometimes crackles. That faint snap is electricity. Rub your feet on a carpet and touch a doorknob, and it stings. That spark can be thousands of volts. It has been with us the whole time, in the amber and the lightning and the nerves, long before anyone had a wire or a switch. And here is the strange part, the part we are going to sit with tonight. Almost everything you picture when you think of electricity is a little bit wrong. You probably imagine tiny things flowing through a wire, little balls of charge, racing along like water down a pipe. It is a good picture. It is the one we are all taught. But it is not quite what happens. The little things barely move. What actually carries the energy is not really them. And even the direction we say the current flows was guessed, long ago, by a man who got it backward, and we never fixed it. So the honest answer to the simple question, what is electricity actually made of, is stranger and quieter than the picture in your head. Tonight, we are going to sit with all of it, gently, the parts that make clean sense, and the parts that still puzzle the people who study them. You don't need to follow every step. You don't need to hold anything in your head. If you drift off somewhere in the middle, that is completely fine. The electricity in you will keep running while you sleep. Your heart will keep its beat. The ideas will still be here in the morning. And so will you. So let's start where the story actually starts. Not with a wire, and not with a battery. Let's start with a stone. A soft golden stone, warm to the touch, that people have loved for a very long time. Amber. Amber is not really a stone. It is tree sap, resin that oozed from ancient pines and then sat in the ground for millions of years until it hardened into a warm gold jewel. Sometimes there is an insect trapped inside, a mosquito or an ant, held perfectly still since before there were people. The ancient Greeks prized it. They carved it and wore it. And somewhere along the way, someone noticed that amber does something odd. Rub it. Rub a piece of amber on a bit of wool or fur, and it changes. It starts to pull at things. Little bits of dust, a thread, a dry leaf, a wisp of hair, all lift and cling to it. The amber reaches out and grabs at light things without touching them. To an ancient eye, that was close to magic. A dead gold stone, warmed by rubbing, suddenly hungry, pulling straws toward itself across a small gap of empty air. The Greek word for amber was electron. Sit with that word for a moment. It is the root of every electric thing you own. The lamp, the phone, the wire in the wall, the whole humming electric world. All of it is named after a piece of rubbed tree sap that picks up dust. A philosopher named Thales, around 600 years before the Common Era, is usually credited with writing about this pull, though the record is thin. For the next 2,000 years, that was more or less the whole of the science. Amber, when rubbed, attracts. Nobody knew why. Nobody could do much with it. It was a parlor trick, a curiosity, and it sat almost untouched for 20 centuries. There was a second strange stone too, and for a long time people muddled the two together. That was lodestone, a naturally magnetic rock that pulls on iron. So you had two mysterious pulling stones. Amber, which grabs light things when you rub it, and lodestone, which grabs iron all on its own. They seemed like cousins, two kinds of the same odd reaching out, and telling them apart, seeing that they were two different forces and not one, turned out to be the first real step. The man who took it was an Englishman and a doctor to a queen. His name was William Gilbert. He was physician to Queen Elizabeth I, and in the year 1600, he published a careful book about magnetism called On the Magnet. Gilbert did something that was still rare then. He tested things patiently instead of just repeating the old books, and he saw clearly that the amber effect and the lodestone effect were not the same. Magnetism pulled only certain things, mostly iron, and needed no rubbing. The amber effect pulled almost anything light, but only after you rubbed it. Different rules, different force. He studied many other substances too, not just amber, and found that a whole family of them behaved the same way when rubbed. He needed a word for that family, and he reached back to the Greek. From electron, amber, he coined a new Latin word for these amber-like substances: electric. That is the moment the word enters the world. 400 years ago, in a book about magnets, named after a stone that catches dust. For a while after Gilbert, the science crept along slowly. People built small machines to make the amber effect stronger, spinning globes of sulfur or glass that you held your hand against as they turned, so the rubbing happened faster and the charge built up bigger than any hand could manage. Sparks began to appear, little cracks of light and sound, jumping from the machine to a knuckle. And two discoveries came out of this tinkering that shaped everything after, because they revealed that this electric stuff has a structure, that it obeys rules, that it is not just a vague reaching, but something with parts. The first was that electricity can move, and that some materials let it move while others hold it still. An Englishman named Stephen Gray, an amateur working in near poverty, found in the early 1700s that if he charged one end of a long, damp thread, the far end became charged too. The electricity had traveled. It ran along some things, like metals and moist string, easily. It refused to run along others, like silk and glass. We call the first kind conductors and the second kind insulators, and that simple split is still with you everywhere. The copper in your walls is a conductor. The plastic wrapped around it is an insulator, keeping the electricity in its channel. Gray had found the difference by playing with thread. The second discovery was stranger, and it took the amber picture apart. A French experimenter named Charles Dufay noticed that electricity does not come in only one kind. There were two. He found that a charged piece of glass and a charged piece of amber did opposite things. Bring two charged bits of glass together, and they push apart. Bring two charged bits of amber together, and they also push apart. But bring the charged glass near the charged amber, and they pull toward each other. Two flavors of electricity, and they behaved like opposites. Same kind repels. Opposite kinds attract. That rule is the whole reason matter holds together, though nobody knew that yet. For now, it was just a beautiful, puzzling pattern in the sparks. Then someone found a way to store it, and gave everyone a fright. In the 1740s, experimenters in Germany and in the Dutch city of Leiden were trying to catch electricity in a jar, quite literally. The device came to be called the Leyden jar, and it was simple. A glass jar, lined inside and out with metal foil, with a rod and a chain running down into it. You charged it up from a spinning machine, and the jar quietly held the charge, waiting. One of the Dutch investigators, Peter van Musschenbroek, charged such a jar and then touched it, and received a shock so violent, he said afterward, he would not take another for the whole kingdom of France. That was the point. People realized this was not a gentle curiosity. The Leyden jar could store a real dangerous amount of electricity and release it all at once through a person in an instant. Now they had a way to save up the sparks and study them. And across the ocean, a printer in Philadelphia was about to become the most famous electrical thinker in the world. His name was Benjamin Franklin. You know him for other things: the founding of a country, the spectacles, the face on the money. But before all of that, Franklin was one of the sharpest experimental minds of his age, and electricity was his great love. In the 1740s and 50s, he threw himself at it, and he brought something new to the subject, a clear and simple idea about what was going on underneath all these sparks and shocks. Franklin proposed that electricity was a single invisible fluid, not two kinds, as Dufay had it, but one, present in everything. When you rubbed amber, he said, you were not creating anything. You were just moving this fluid around. Some objects ended up with too much of it, and some with too little. An object with an excess he called positive. An object with a shortage he called negative. Rubbing simply shifted the fluid from one thing to the other, leaving one with a surplus and the other with a deficit. Charge, in his picture, was never made or destroyed. It was only moved. And that idea that the total amount of charge stays fixed and only gets shuffled around turned out to be exactly right. We still call it the conservation of charge. It is one of the deepest rules in physics, and a printer guessed it from watching sparks. But Franklin made one choice that has haunted every student since, and it is the first piece of our answer to why electricity is not quite what you think. He had to decide which way the fluid flowed. When electricity moved through something, which direction was it going? He had no way to know, so he guessed. He decided that the fluid flowed from the positive object to the negative one, from the surplus to the shortage. It was a 50-50 guess, reasonable, clean, and it was backward. When we finally understood, more than a century later, what actually moves in a metal wire, it turned out to be tiny negative particles, and they flow the other way, from negative to positive, opposite to Franklin's arrow. But by then, his convention was everywhere, in every book and every diagram, far too late to flip. So to this day, we draw electric current flowing one way, while the actual particles flow the other. Every electrical engineer alive learns this and just lives with it. The current in the diagram and the electrons in the wire run in opposite directions, all because of one honest guess in Philadelphia 2.5 centuries ago. And then there is the kite. It is the most famous experiment in the history of electricity, and like most famous experiments, the popular version is a little too tidy. Franklin suspected that lightning was not some divine fire but simply electricity, the same stuff as his sparks, only enormous. To test it, the story goes, he flew a kite into a thunderstorm in 1752 with a metal key hanging from the wet string and drew electric sparks from the key, proving lightning was electrical. Something like this did happen. But hold the drama loosely. If Franklin had truly let his kite be struck by a full bolt of lightning, he would very likely have died, as at least one person who copied him soon did. What he actually did was subtler and safer, drawing off the gentle charge that builds in a stormy sky, not taking a direct strike. Either way, the conclusion stood. Lightning was electricity. The spark from the amber and the bolt that splits a tree were the same force, differing only in scale. Franklin went on to invent the lightning rod, a simple pointed metal spike that quietly guides a strike safely down into the ground, and it has protected buildings ever since. It may be the first time understanding electricity saved a single human life. It would not be the last. So by the middle of the 1700s, electricity was real, storable, and known to be the same as lightning. But it was still a thing of sudden sparks and shocks. A jolt, and then nothing. You charged a jar, you discharged it, and it was over in an instant. Nobody had a way to make electricity flow steadily, to keep it moving in a gentle, continuous stream. And without that, there could be no electrical world. A single spark cannot run a lamp. What changed everything came, of all places, from a dead frog. And it started as an argument between two Italians who were both, in a way, right. The first was Luigi Galvani, an anatomist in Bologna. In the 1780s, while dissecting frogs, he noticed something that stopped him cold. When his metal scalpel touched the nerve of a frog's leg, the dead leg twitched, kicked as if briefly alive. Galvani found he could make the legs jerk again and again with a touch of metal, and he came to believe he had found something profound. He thought the electricity was inside the frog, a special life force he called animal electricity, stored in the living tissue and released by the touch. It was a beautiful idea, the spark of life made literal, and it was wrong, though not entirely. His countryman Alessandro Volta thought Galvani had misread his own experiment. Volta noticed that the twitch happened when two different metals were involved, touching the frog and each other. So maybe, he thought, the electricity was not coming from the frog at all. Maybe the frog was just a detector, a sensitive wet gap, and the real source of the electricity was the two different metals themselves. Who was right? Was the electricity in the animal or in the metals? The argument ran for years, and settling it drove Volta to build something entirely new. If metals were the source, he reasoned, he could make electricity with no animal at all. He stacked discs of two different metals, zinc and copper, one on top of another, and separated each pair with cloth soaked in salty water. A stack of metal, brine, over and over, into a tall pile. And the pile worked. It pushed out a steady, continuous flow of electricity, the first current that did not come in a single burst, but kept going, on and on, as long as the pile held together. Volta had built the first battery, around the year 1800, and it changed the whole science overnight. For the first time, people had a reliable source of flowing electricity, a current they could keep running while they watched. Everything before had been the study of sparks. Now, at last, electricity could be a river instead of a lightning strike. The battery is still called a voltaic pile in his honor, and the unit of electrical push, the volt, carries his name every time you read it off a battery. Galvani was not wholly wrong either. Our nerves really do run on electricity, the very signals moving in you right now. But the frog leg had been a detector, not a source, exactly as Volta thought. Before we follow the current outward into magnetism and fields, it helps to have three simple words for what a current actually involves, because they are the words the whole electrical world is built on, and they are gentler than they sound. When electricity flows, three things matter: how much is flowing, how hard it is being pushed, and how much the path resists it. That is really all. And there is an old comparison that makes it easy, a comparison to water in a pipe, and though it is not perfect, it is close enough to rest on. Think of water flowing through a pipe. The amount of water going past each second is like the current, how much electricity is flowing, measured in those amps named after ampere. The pressure pushing the water along is like the voltage, the push, measured in volts, named after Volta, whose pile we just built. And the narrowness of the pipe, how much it fights the flow, is like the resistance, measured in a unit called the ohm. That last name belongs to a quiet German schoolteacher named Georg Ohm, who in the 1820s worked out the simple relationship between these three things. He found that they locked together in a plain and reliable way. For a given push, a greater resistance means a smaller flow in an exact and predictable proportion. Double the push, and you double the flow. Double the resistance, and you have it. It is one of the most useful rules in all of engineering, so simple a child can learn it, and every electrician and every circuit ever built rests on it. We call it Ohm's law. And here is the human part, the part that keeps happening in these stories. When Ohm first published his careful work, it was ignored and even mocked. His superiors thought it too simple or too abstract, and it hurt his career for years. He was a school teacher without a grand position, and the recognition came slowly, long after he had earned it. Only later was he honored, and the unit of resistance given his name, so that now every time anyone anywhere measures a resistance, they say his name without thinking. The overlooked schoolteacher won in the end, the way the overlooked so often do in this particular story. And it is worth pausing, just for a breath, on where the push in a battery actually comes from, because Volta never quite understood it himself. The steady pressure a battery provides is not really electrical in origin, it is chemical. Inside the battery, a slow chemical reaction is taking place, one substance giving up electrons and another taking them, and that reaction is what pumps the charge, what does the pushing, what keeps the current flowing. A battery is a small chemical engine, quietly disassembling itself to keep the electrons moving, which is why a battery eventually goes flat. It is not that the electricity runs out, it is that the chemicals are used up. The reaction finishes, the pump stops, and the current dies. Every battery you have ever thrown away was simply a little chemical fire that finally burned down to nothing. And here is a lovely thing. Nature built a battery long before Volta did. There is a fish that makes its own electricity. It is called the electric eel, though it is not really an eel, and it lives in the muddy rivers of South America. It can deliver a jolt strong enough to knock down a horse. Hundreds of volts, from a living animal, in the water. For a long time, nobody understood how. Then people looked inside and found something remarkable. Most of the eel's long body is not for swimming. It is a battery. Stacked down its length are thousands of thin, flat cells, each one a tiny biological pump of charge. On its own, each cell makes only a whisper of electricity, about the same faint push as a single nerve. But they are stacked in a long series, thousands of them, end to end. And when the eel fires, they all switch on at once, and their little pushes add together, one on top of another, all down the line. Thousands of small pushes, stacked, become one enormous one. That is exactly what Volta did with his disks of metal and brine. He stacked small sources to make a big one. The eel got there first, by many millions of years, growing a voltaic pile inside its own body out of living cells. Think about that for a moment, softly. When Volta built the first battery, he was, without knowing it, copying a fish. The same trick, stacking many weak cells into one strong current, had been swimming in the rivers of the Amazon the whole time. The eel uses its jolt to stun the small fish it eats, and to feel its way through the murky water, sensing the world through electricity the way you sense it through light. It is a creature that lives partly in an electrical sense we do not have, and it is a reminder that electricity was never really a human invention. We did not make it. We found it. It was in the amber, and in the storm, and in our own nerves, and swimming quietly in the dark rivers, long before anyone thought to give it a name. Now the discoveries came faster, because now there was a steady current to work with. And the next one was an accident in front of a class that joined two great forces of nature together. For a long time, remember, electricity and magnetism had been kept firmly apart. Gilbert himself had insisted they were different. A charged rod and a compass needle seemed to have nothing to do with each other. But in 1820, a Danish physicist named Hans Christian Ørsted was giving a lecture demonstration with a wire carrying a current from a battery, and a compass happened to be lying nearby on the bench. When he switched the current on, the compass needle twitched. It swung and pointed sideways, away from north. Ørsted stared. Why would an electric current move a magnet? The two were supposed to be unrelated. He tried it again and again, and it held. A current in a wire pushes on a compass needle as surely as a magnet would. The moving electricity was making magnetism. The needle did not point at the wire either, which was the strange part. It tried to line up in a circle around the wire, as if the wire were wrapped in invisible rings of magnetic force. This was a genuine shock to the whole field. Two forces that everyone had held apart for centuries turned out to be secretly linked. Electricity could make magnetism. The hidden connection was out. A French physicist named André-Marie Ampère heard the news within weeks and threw himself at it, working out the mathematics of how currents and magnets push on each other with astonishing speed. He showed that two wires carrying current will themselves attract or repel, with no magnet needed at all, just two flows of electricity pushing on one another through the empty space between them. The unit of electric current, the amp, the one that measures how much is flowing, is named for him. So the picture was widening. Electricity was not only sparks and shocks and steady currents. It reached out sideways into magnetism. And that raised an obvious question, the kind that drives science forward. If a current can make magnetism, can magnetism, run the other way, make a current? Could you turn the handle backward? That question fell to a quiet, self-taught man who had started life as a bookbinder's apprentice and who would become perhaps the greatest experimenter who ever lived. His name was Michael Faraday, and his life is one of the loveliest in all of science. He was born poor in 1891 in London, the son of a blacksmith. Forgive me, in 1791. He had almost no schooling. As a boy, he was apprenticed to a bookbinder, and that turned out to be his university because he read the books that passed through his hands. He read one on chemistry and one on electricity, and he was hooked. He went to public science lectures, took careful notes, bound them into a book, and sent them to a famous scientist as a way of begging for a job. It worked. He became a laboratory assistant, and in time, he outshone them all. He never learned much mathematics. He thought in pictures instead, and those pictures changed physics forever. Faraday took up Ørsted's question and turned it around. A current makes magnetism. Could magnetism make a current? He tried for years and kept failing because he missed one crucial thing. A still magnet does nothing. But in 1831, he found the secret. It was motion. When he pushed a magnet into a coil of wire, a current flowed in the wire. When he pulled it back out, the current flowed the other way. When the magnet sat still, nothing. The current appeared only while the magnet was moving, while the magnetism through the coil was changing. This is called electromagnetic induction, and it is, quietly, one of the most important discoveries ever made. Because almost all the electricity in your home right now is made this way. Every power plant, whatever burns or falls or blows to run it, is in the end just spinning magnets past coils of wire. Coal, gas, nuclear, wind, water, all of it does the same final thing. It moves a magnet near a wire, exactly as Faraday did on his bench, only vastly bigger. When you flip a switch tonight, you are drawing on Faraday's twitch of a magnet in a coil, repeated in a turbine somewhere, 60 times a second. But Faraday gave us something even deeper than the generator, and it is the idea that finally starts to answer what electricity really is. He could not accept the old notion that a magnet or a charge simply reaches across empty space and grabs a distant thing, with nothing in between. Franklin's fluid, Newton's gravity, all of it had this uneasy action at a distance, a pull crossing a gap of pure nothing. Faraday looked at the patterns iron filings make around a magnet, those graceful curved lines that arc from pole to pole, and he came to believe they were showing him something real. He thought the space around a magnet or a charge is not empty at all. It is filled with something, a condition, a tension, reaching out in every direction. He called them lines of force. We now call the whole thing a field. This is worth slowing down for, because it is the heart of the matter. A field means that a charge changes the space around it. It fills the surrounding emptiness with an invisible influence, strong up close, fading with distance, pointing in a direction at every single point. Another charge, placed nearby, does not feel a magic pull from across the void. It feels the field that is right there, where it sits, in its own immediate spot. The first charge talks to the space next to it. That patch of space talks to the next. And so the influence travels outward, hand to hand, through the field, rather than leaping instantly across the gap. Electricity and magnetism, in Faraday's vision, are not really about the little charged objects at all. They are about the fields those objects create, filling all the space around them. The objects are just the sources. The field is the thing. He could not prove it with mathematics. He simply saw it, in the curved lines of iron filings, with the eyes of a man who thought in pictures. It took a mathematician to turn Faraday's vision into hard equations, and to reveal, hidden inside them, the most astonishing thing of all. That light itself is made of these fields. The mathematician was James Clerk Maxwell, a Scottish physicist, one of the deepest minds the subject has ever had, and he revered Faraday. Where others saw an unschooled experimenter with a strange notion of lines in the air, Maxwell saw genius. He set out to write Faraday's pictures in the language of mathematics. And in the 1860s, he did, in a set of equations that describe exactly how electric and magnetic fields behave, how they are made, how they curl around each other, how they change. There are 4 of them in the modern form. They are, to a physicist, some of the most beautiful lines ever written, and they hold the entire behavior of electricity and magnetism in a few compact strokes. But the equations held a secret Maxwell almost did not believe at first. When he worked through them, he found that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. So imagine you jiggle a charge. It makes a changing electric field. That changing electric field makes a magnetic field. That changing magnetic field makes another electric field, a little further out. And on, each one giving birth to the next, leapfrogging outward through space, a self-sustaining ripple of electricity and magnetism, taking turns holding each other up. A wave made of pure field, needing no substance to travel through, able to cross empty space on its own. Maxwell could even calculate how fast this wave would move. The equations gave a speed, built out of 2 numbers already measured in the laboratory, numbers about how strong electric and magnetic forces are, and when he put those numbers in, the speed that came out was the speed of light. Sit with that for a moment, because it is one of the great moments in the history of thought. Maxwell was doing electricity and magnetism, sparks and coils and compasses, and out of his equations fell the exact speed of light, a number that had been measured by astronomers watching the moons of Jupiter. That could not be a coincidence. There was only one honest conclusion, and Maxwell drew it. Light is an electromagnetic wave. Light is electricity and magnetism, weaving together and rippling through space. The glow of the lamp, the warmth of the sun, the colors of everything you have ever seen, all of it is the very same force as the spark from the amber, only vibrating fast and flying free. This is one of the deepest unifications ever found. Two ancient mysteries, electricity and light, revealed as one thing. And it means that when you finally understand electricity, you also understand light and radio and the warmth on your skin in the sun. They are all fields, rippling, at different speeds of trembling. Maxwell died in 1879, at only 48, before he could see his waves proven. A few years later, a young German named Heinrich Hertz made them in his laboratory, on purpose, invisible electromagnetic waves flying across his room, the first radio waves ever deliberately sent and caught. The whole wireless world grew from that. And still, notice, nobody yet knew what actually carried the charge. Maxwell had the fields. He did not have the particle. That last piece was hiding inside the atom, and finding it would break the atom open. To find the thing that carries electricity, scientists had to look inside a strange, glowing tube. In the late 1800s, physicists were playing with sealed glass tubes that had most of the air pumped out, with a metal plate at each end wired to a high voltage. When they switched it on, the tube glowed, and a mysterious ray traveled from the negative plate to the positive one. They called these cathode rays, after the negative plate, the cathode. Nobody knew what the rays were. Some thought they were a kind of light, a wave. Others thought they were tiny particles. The argument went back and forth for years. What were these rays really? Were they waves in the ether? Or were they little pieces of something flying across the tube? The man who settled it was Joseph John Thomson, known as J.J. Thomson, working at the Cavendish Laboratory in Cambridge, the same Cavendish family we met weighing the Earth. In 1897, Thomson did a careful set of experiments on these rays. He bent them with magnets. He bent them with electric fields. He measured how much they bent, and from the bending he could work out something about the things that made up the ray. And what he found was staggering. The rays were made of particles, tiny ones, and each one carried a negative electric charge. But their mass, the amount of stuff in each one, was almost nothing. They were nearly 2,000 times lighter than the lightest atom known, the hydrogen atom. Nothing that small had ever been found. Everyone had thought the atom was the smallest thing there was, indivisible, the very bottom. Its name even means uncuttable, and here was Thomson, holding evidence of something far smaller, a piece that seemed to come from inside the atom itself. He had discovered the electron, the actual particle of electricity, the thing that had been doing all of it, all along. The pull of the rubbed amber, the shock of the Leyden jar, the current in Volta's pile, the signal in your nerves. All of it was these unimaginably tiny negative specks, far smaller than atoms, present in all matter. When you rub amber with wool, you are wiping a thin film of electrons from one onto the other. When current flows in a wire, electrons are drifting through it. Franklin's invisible fluid was real, and it was made of countable little particles, and each one was an electron. Thomson had reached inside the atom and pulled out the carrier of charge. For that, he won the Nobel Prize. and he found something even more unsettling in passing. If atoms contain these tiny negative pieces, then the atom is not the bottom. The atom has an inside. Matter has parts within parts, and the electron was the first of them ever seen. There was one number still missing, the charge on a single electron, how much electricity one of them carries. That was pinned down by an American physicist named Robert Millikan in a patient and beautiful experiment around 1910. He sprayed a fine mist of tiny oil drops into a chamber, and some of them picked up a few stray electrons and became slightly charged. Then he used an electric field to hold a single tiny drop suspended in the air, floating, balanced between gravity pulling it down and the electric force holding it up. By watching one drop hang and float and measuring it, he could work out the charge it carried. And he found that the charge always came in whole multiples of one basic amount. Never half of it, never a third. Always one lump or two lumps or three of the same smallest unit. That smallest unit was the charge of a single electron. Electricity was not smooth. It was grainy. It came in indivisible pieces, one electron at a time, and Millikan had measured the size of the grain. So now, at last, we seem to have a clean picture. Electricity is a flow of electrons, tiny negative particles streaming through a wire. And that picture is where the story usually stops, and it is the picture we are now going to gently take apart, because the truth is stranger, and honestly, more beautiful. Because if you ask how fast those electrons are actually moving through the wire when you turn on a light, the answer is almost comical. They crawl. They move slower than you do when you are being lazy. Let me show you what is really inside a copper wire. Copper is a metal, and in a metal the outer electrons are not tied to any one atom. They drift free, a vast sea of loose electrons sloshing around at random, jittering at incredible speeds in every direction, but going nowhere on average, like a swarm of gnats hovering over a pond. There are almost unimaginably many of them, packed into even a short piece of wire, more than the number of stars in the visible universe, all crammed into a length you could hold in your hand. That sea is always there, in every wire, whether the current is on or off. Now you connect a battery. The battery sets up an electric field along the wire, a gentle push, and that whole sea of electrons begins, on top of its wild random jittering, to drift very slowly in one direction. That slow collective drift is the electric current. How slow is the drift? This is the part that surprises everyone. In a typical wire carrying a normal household current, the electrons drift along at something like a few feet per hour. Slower than a snail. Slower than honey off a spoon. If you could paint one electron bright red and watch it, and you switched on a lamp across the room, that red electron near the switch would take hours to amble its way to the bulb. So here is the puzzle. If the electrons crawl that slowly, why does the light come on the instant you flip the switch? You do not wait hours in the dark for the electrons to arrive. The room lights up at once. How? If the messengers are that slow, what is delivering the message? The answer is the key to the whole thing, and it takes us right back to Faraday and his fields. When you flip the switch, you do not wait for electrons to travel from the switch to the bulb. You do not need to. The wire is already full of electrons, everywhere along its length, right up to the bulb, sitting there the whole time. Flipping the switch sends out an electric field, a signal, and that signal races down the wire at nearly the speed of light. It tells every electron, all along the wire, to start drifting, more or less at once. The electrons right next to the bulb start moving through it immediately. They were already there. So the bulb lights instantly, not because anything traveled the distance quickly, but because the whole line was already loaded, and the order to march arrived almost instantly, everywhere at the same time. It is less like water arriving through a hose and more like a train, where every car lurches forward the moment the front one does, because they are all coupled together already. The electrons barely move. The field does the racing. And it gets stranger than that, because even the energy, the actual power that heats the filament and makes the light, does not travel through the wire the way you would think. You might picture the energy being carried along inside the wire, handed from electron to electron down the copper, like a bucket brigade passing water. That is not really where the energy goes. According to Maxwell's own equations, the energy flows in the field, in the space around the wire, not inside the metal at all. The wire mostly just guides it, the way the banks of a river guide the water without being the water. The energy travels in the invisible electric and magnetic fields that surround the wire in the empty space just outside the copper, and it dives into the wire only where it is needed, to be spent as heat and light. The copper is a channel. The energy rides alongside it, in the field. This is genuinely hard to believe the first time, and physicists argued about it, and it is nonetheless true and well tested. The power reaching your lamp is not pushed through the metal by crowding electrons. It flows in through the fields around the wire and sinks into the bulb. The electrons in the wire are more like a long line of people passing a message by each nudging the next, while the actual energy glides along outside them, in the space they define. So the little particles you imagined carrying the electricity are barely moving, and the energy is not even really traveling in them. It is in the field, again, always the field, the thing Faraday saw in the iron filings and could not prove. There is one more piece that undoes the simple picture completely, and it is sitting in your walls right now. The electricity in your home is not a steady flow in one direction. It is what we call alternating current, and it does something almost funny. In alternating current, the electrons do not travel along the wire at all, not even slowly. They just jiggle. They shuffle a tiny bit one way, then a tiny bit back the other way, then forward again, back again, swinging in place 60 times every second in some countries, 50 in others. Back and forth, going absolutely nowhere. Over a whole night, over a whole year, the average electron in your lamp cord ends up exactly where it started. It has never left home. It has only trembled. And yet the light shines all night, steady and bright, because the energy is in the field, and the field does not care that the electrons are only shivering in place. The push travels. The electrons stay. That quiet fact that your home runs on trembling and not on travel was the winning side of one of the strangest fights in the history of technology, and it is worth a gentle detour, because it is a good story, and it explains the wire in your wall. In the 1880s, when electricity was first being brought into homes and streets, there were two rival ways to send it, and two rival camps, and they went to war over it. On one side was Thomas Edison, the famous inventor, who had built his early electrical empire on direct current, the steady one-direction flow of a battery, the simple kind. On the other side was a way of sending electricity as alternating current, the jiggling kind, the kind that swings back and forth and goes nowhere. And the great champion of alternating current was a brilliant, eccentric Serbian-American inventor named Nikola Tesla, backed by the industrialist George Westinghouse. Why did it matter which one won? It came down to distance, and it came down, once again, to Faraday. Direct current is hard to send very far. It leaks away its energy as heat over long wires, and Edison's system needed a power station every mile or so, which could never light a whole country. Alternating current had a decisive trick that direct current lacked, and the trick was Faraday's induction, the moving magnetism that makes a current. Because alternating current is always changing, always swinging, it is always inducing, and that means you can use a simple device called a transformer to step its voltage up very high for the long journey down the wires, which loses far less energy, and then step it back down to something safe before it enters a house. Direct current could not do this easily. Alternating current could. So it could be sent across hundreds of miles from a single great power station, which is exactly what a country needs. The fight got ugly and rather dark. To frighten the public away from alternating current, Edison's camp staged demonstrations showing that the high voltages could kill, publicly electrocuting animals to make the point, and even quietly helped make sure the first electric chair used alternating current, so the method would be linked in people's minds with death. It did not work. The advantages of alternating current were simply too great. The turning point came at the very end of the century, when Westinghouse and Tesla won the contract to harness the enormous power of Niagara Falls and sent that electricity as alternating current all the way to the city of Buffalo, over 20 miles away. It worked beautifully. The war was effectively over, and that is why, to this day, the electricity in your walls is alternating current, why the electrons in your lamp only ever tremble in place and never travel, and why Tesla, who died alone and nearly forgotten, is now a household name. Every socket in your home is a quiet monument to the side that won. Once electricity could be sent over long distances, it did something it had never done before. It carried messages, and this is where the electrons crawl and the field's speed matter most, so it is worth a moment. Long before the lights came on, going back to the 1840s, people had built the telegraph, a way of sending pulses of electricity down a wire and clicking them out at the far end, in the pattern of dots and dashes worked out by Samuel Morse and his colleagues. For the first time in all of history, a message could travel faster than a horse, faster than a ship, nearly as fast as light itself. A person in one city could tap out words, and a person hundreds of miles away could read them almost the same instant. It collapsed distance in a way nothing ever had. And then they did something almost unbelievable for the time. They laid a cable along the bottom of the ocean, all the way across the Atlantic, from Ireland to Newfoundland, to join two continents by wire. The first attempts, in the 1850s and 60s, were heartbreaking. Cables snapped and were lost in the deep. One worked for a few weeks and then went dead. It took years of failure and enormous expense and a great deal of stubbornness before a lasting cable finally held, and a message could cross the whole ocean in minutes instead of the weeks a ship would take. Notice what was really happening in that cable, thousands of miles long, lying in the cold dark of the seabed. The electrons in it were barely creeping, but the signal, the pattern, the message, raced across the ocean floor at a good fraction of the speed of light, because the field carried it, not the electrons. The very thing we found in the little wire to the lamp was there in the great cable under the sea. The stuff stays nearly still. The message flies. A person's words crossed an ocean in the fields around a wire, while the electrons inside it hardly moved at all. So gather up what we have found and hold the strangeness of it gently, because this is the answer to the question we started with. What is electricity actually made of, and why is it not the electrons you think? It is made of electrons, yes, but they barely move. It is made of a current that we draw flowing one way while the electrons go the other, because of Franklin's old guess. It is made of energy that travels not in the particles, but in the fields in the space around them. And in your home, the electrons never even go anywhere. They just quiver. The thing you call electricity is far less like water in a pipe and far more like a wave passing through a crowd where nothing travels the distance except the pattern, the disturbance, the message. The stuff stays put. The wave moves through it. That is closer to the truth of it than any picture of little balls racing down a tube. And if you push down one more level, past the electron itself, the picture dissolves into something even gentler and stranger, which is where the deepest physics of the last 100 years has taken us. Because we have been talking about the electron as a tiny ball, a little grain of charge. But that is not really what it is either. In the modern understanding, the one that came out of the strange new physics of the 20th century, the electron is not a solid speck at all. It is a ripple, a small, stable disturbance in an invisible something that fills all of space, called the electron field. Here is the idea, as softly as it can be put. Physics now thinks the universe is filled, everywhere, with fields. Not just the electric and magnetic fields, but a field for every kind of particle. There is an electron field, spread through all of space, present in this room, present in you. And a particle, an electron, is simply a place where that field is bunched up into a little quivering knot of energy, a ripple that holds together and moves along. Every electron in the universe is a ripple in the same single field, which is why every electron is exactly identical to every other. They are all the same kind of wave in the same ocean. When electricity flows, you can think of it as ripples moving in that field. When light travels, it is ripples in the electromagnetic field. Everything is fields, and the particles are just the ways the fields gather themselves into countable lumps. And the force itself, the push and pull between charges, has a particle too, in this picture, though a fleeting kind. Two electrons repel each other. How do they feel each other across the gap? They trade photons, little packets of the electromagnetic field, flung back and forth between them, carrying the force. The same photon that is a particle of light is also the messenger of all electricity and magnetism. When two charges push apart, in the deepest description we have, they are tossing photons between them, and the tossing is the force. So the amber pulling the dust, the shock from the doorknob, the current in your nerves, the light of the lamp, all of it, at the very bottom, is one field talking to itself by passing little quanta of light. It is a strange and lovely unity. The whole electric world, reduced to ripples exchanging ripples. This deep theory has been tested to a precision almost beyond belief, matching experiment to more decimal places than almost anything humans have ever measured. It is, as far as we can tell, how the world actually works. And it still leaves the simplest question not fully answered. Let's go back into the wire for a moment, because there is a gentle question we skipped, and the answer is soothing in its own way. If a metal is full of these free electrons, drifting when you push them, why does a wire get warm when current flows? Why does the filament in an old bulb glow hot? Where does that heat come from? The answer is that the drifting electrons do not have a clear road. As they try to move along, they keep bumping into the atoms of the metal, which are not sitting perfectly still. The atoms are jiggling with their own warmth, arranged in a great orderly lattice, and the drifting electrons collide with them, over and over, jostling them, handing over a little energy with each bump. That handed over energy is heat. That is all electrical resistance is. It is the electrons bumping their way through a crowd of trembling atoms, warming everything as they go. A toaster, a heater, an old light bulb, all of them are just wires chosen to make the electrons bump hard, so the bumping turns into warmth and light. So resistance is friction, in a sense, the electrons scraping through the lattice. And you might think that is simply how it must be, that any flow of electricity must warm the wire, must lose something to all that bumping. For a long time, everyone thought so. But nature had a quiet surprise waiting, and it is one of the most beautiful things in all of physics. If you take certain metals and cool them down, colder and colder, toward the deepest cold there is, something astonishing happens. At a certain temperature, all at once, the resistance vanishes. Not gets small, vanishes, drops to exactly nothing. The electrons stop bumping. They flow through the metal with perfect ease, forever, losing no energy at all. This is called superconductivity, discovered in 1911 by a Dutch physicist named Heike Kamerlingh Onnes, who had learned to make things colder than anyone before him. In a superconductor, a current once started will flow around and around a loop for years, for a human lifetime, without a battery, without fading, without warming anything, because there is nothing to slow it. It is as close to perpetual motion as the universe ever allows. And why does it happen? This is the loveliest part. Down in that deep cold, the electrons, which normally ignore each other or push apart, quietly find partners. They pair up, 2 by 2, bound together in a gentle way through the lattice, and once paired, the whole crowd of them falls into a single shared state, moving in perfect step, as one. A crowd of individuals, each bumping and stumbling, becomes a single smooth thing that glides. They no longer collide with the atoms one at a time, because they are no longer acting one at a time. They move together, and nothing can trip them. It took until 1957 for anyone to explain it, and the explanation is pure quantum physics, the strange rules of the very small written large enough to hold a current in your hand. These superconductors are real, and they are working right now, cooled deep inside the great machines that scan bodies in hospitals and inside the largest particle colliders on Earth. Electricity, flowing without friction, forever, in a cold and perfect silence. And here is a thought to rest on before we go deeper. The electron, this tiny thing we have been chasing all night, does far more than run through wires. It builds the entire material world. Everything solid, everything you can touch, everything you are, is held together by electrons. When two atoms join to make a molecule, it is their electrons that do the joining, shared between them or handed from one to the other, a kind of electrical handshake. Every bond in every substance, the water in your glass, the wood of the door, the bone and skin and muscle of your own body, is electrons, arranged and shared. All of chemistry, the whole of it, is really just the behavior of electrons around atoms. Life itself is electrical chemistry. You are a structure built and held by these little ripples of charge, and the signals that run you are electrical too, though in a gentler, wetter form than a copper wire. In your nerves, the current is not free electrons streaming along metal. It is charged atoms, ions, sloshing in and out through the walls of your nerve cells, a wave of charge moving down the nerve like a line of dominoes falling. But it is the same fundamental thing, charge in motion, electricity, obeying the same rules that Franklin and Faraday and Maxwell uncovered. When you decide to move your hand, a pulse of electricity runs down your arm to the muscle. When light lands in your eye, it becomes an electrical signal that travels to your brain. When your heart beats, It is answering a small electrical wave that sweeps across it, and a machine can read that wave through your skin. You are not a thing that uses electricity. You are, in a real sense, a thing made of it, a slow, warm pattern of moving charge, thinking, right now, about moving charge. So the amber that catches dust and the thought in your head are the same story, told at different scales. That is the quiet unity underneath all of it. The rubbed stone, the stored shock in the jar, the current in the pile, the field in the coil, the wave that is light, the electron in the wire, the bond in the molecule, the pulse in the nerve. All of it is charge and fields and the endless conversation between them. It is one of the great unifications the human mind has found, that so many separate wonders turned out to be a single thing, wearing different clothes. And yet, when you get all the way down to the bottom of it, to the very thing itself, to charge, there is a question we still cannot answer. We can tell you everything electricity does. We still cannot quite tell you what charge is. We will come back to that deepest question. But before we do, look up for a moment, in your mind, at the sky, because the grandest display of electricity in the world is the one Franklin chased, and we understand it far better now than he did. Lightning. It is worth knowing what actually happens in a bolt, because it is stranger and slower and more delicate than the sudden flash makes it seem. It begins inside a storm cloud, with a gentle violence. Up in the tall, dark thundercloud, water drops and ice crystals are churned up and down by fierce winds, and as they tumble and collide, they rub against each other, and charge is scraped from one to another, exactly like amber on wool, only vast. The lighter bits tend to carry their charge to the top of the cloud, and the heavier bits gather the opposite charge lower down. So the cloud slowly separates into a positive region and a negative region, a giant Leyden jar built of air and ice, storing an enormous charge, straining against the gap. The pull grows and grows until the air itself can no longer hold the two apart. Then comes the part almost no one sees, because it happens in a flicker. The bolt does not leap down in one clean stroke. First, a faint, branching finger of charge, called the stepped leader, pushes down from the cloud toward the ground in a series of quick jumps, feeling its way, forking, searching, far too dim and fast for the eye to catch. As it nears the ground reaches up to meet it. Faint streamers rising from trees and roofs and blades of grass toward the descending finger. When they touch, a channel is complete, a conducting path from cloud to earth. And then, the real stroke fires. A huge surge of charge rushes up that channel from the ground to the cloud, the return stroke, blindingly bright, heating the air in an instant to several times hotter than the surface of the sun. That searing heat makes the air explode outward, and that explosion is the thunder. The flash you see leaps upward, from ground to sky, though it happens far too fast for you to tell. Franklin was right, more right than he could prove. It is the same force as the spark from the doorknob. A storm is a great slow machine for separating charge, and the bolt is the moment it snaps back together in a scale of fire. And here is a small kindness in it, for lying in the dark. The whole towering event, the churning cloud, the straining charge, the searching leader, the return of fire, is just the universe doing what the amber does when you rub it, pulling apart what wants to be together and then letting it rush back. There is nothing in a thunderstorm that is not also in the faint crackle of your blanket. Only the size is different. So the next time a storm passes over the house at night, you can lie there and know exactly what it is, and it is nothing to fear. It is only charge going home. And there is a gentler light in the sky that is electrical too, the loveliest one there is, and it comes all the way from the sun. Far above the weather, high over the cold poles of the earth, the sky sometimes fills with soft curtains of green and red and violet light, shifting and folding, silent, slow. The aurora, the northern lights, and the southern ones. For most of history, nobody knew what they were, and people told all kinds of stories about them, spirits and omens and distant fires. What they actually are is electricity, arriving from 93 million miles away. The sun does not only send us light and warmth, it also blows out a constant thin wind of charged particles, electrons and bare atoms, streaming off it in every direction, washing over the whole solar system. Some of that wind reaches the Earth, and when it does, our planet has a shield waiting for it. That shield is the Earth's magnetic field, the same quiet magnetism that turns a compass needle, reaching far out into space all around the planet. It catches most of the charged particles from the sun and steers them, funneling them down toward the two poles, where the field dips down to meet the Earth. And there, high in the thin upper air, those particles from the sun crash into the atoms of our atmosphere and hand over their energy and make them glow. That is all the aurora is. It is the air itself, lit up like the gas in a glowing sign, struck by electricity from the sun and shining with it. The green is oxygen, high up, glowing its particular color. The reds and violets are other atoms, at other heights, each giving off its own shade, the way each element always does. It is a slow, silent, enormous version of the same thing that happens in a humble neon tube, where electricity runs through a gas and makes it shine. So the curtains of the aurora are the sun's electricity, caught by the Earth's magnetism, painting the upper air in the colors of the atoms it strikes. Charge from a star, made visible in the sky. There is something worth resting on there. The same force that lifts a thread toward a piece of amber, that stings your hand at the doorknob, that runs along your nerves, is also the thing that paints those silent lights above the poles, using particles that left the surface of the sun days ago and traveled all this way to glow, briefly, in our sky, before fading. It has nothing to do with you, and it asks nothing of you, and it is happening right now, quietly, over the top of the world, whether or not anyone is awake to see it. There is one more strange thing about charge worth carrying toward sleep, and it came out of pure mathematics from a very quiet man staring at an equation. His name was Paul Dirac, an English physicist of few words, one of the strangest and most brilliant minds of the 20th century. In 1928, Dirac was trying to write an equation for the electron that would obey both the new quantum physics and Einstein's relativity at once. He found one. It is called the Dirac equation, and it is one of the deep jewels of physics. But it had an odd feature. It did not describe only the electron. It seemed to insist that there must also exist another particle, exactly like the electron in every way, with the very same mass, but carrying the opposite charge. A positive electron, a mirror twin. Dirac was uneasy about this. He had not gone looking for a new particle. It simply fell out of the mathematics, unbidden, the way the speed of light fell out of Maxwell's. For a while he was not sure it was real. But in 1932, an American physicist named Carl Anderson, studying the rain of particles that falls on us from space, found it. A track in his detector curving the wrong way. A particle just like an electron but bending as if positively charged. The mirror twin was real. We call it the positron, and it was the first piece of antimatter ever found, a whole shadow world of particles with flipped charge, predicted by an equation before anyone saw it. And antimatter does something haunting and beautiful. When an electron meets its opposite twin, the positron, they do not bounce. They vanish. The two of them annihilate each other completely, and in their place, a flash of pure light, two photons, carrying away all the energy that was locked in their mass. Matter and antimatter, touching, turn entirely into light. It is the most complete transformation there is. So charge comes in two kinds, positive and negative, just as Dufay saw with his glass and his amber so long ago, and the two are mirror images so exact that when they meet, they cancel to nothing but a glow. Why the universe is built almost entirely of one kind, of ordinary electrons and not positrons, so that matter survived at all, and you are here to wonder about it, is itself one of the great unsolved questions. But that is a thread for another night. Tonight, it is enough to know that the little negative speck in the wire has a positive twin, and that when they meet, they become light, and that this was known from an equation before it was ever seen. So now we come back to the question we keep circling, the one at the very bottom. What is charge, actually? We have followed it everywhere tonight. We know charge comes in two kinds, positive and negative. We know like kinds push apart and opposites pull together. We know it is never created or destroyed, only moved. We know it comes in tiny, indivisible lumps, one electron's worth at a time. We can measure it more precisely than almost anything in nature. And if you ask what it is, in itself, why a particle should have this property at all, why the universe should contain such a thing as charge, physics goes quiet. We can tell you everything it does. We cannot tell you what it is. It is simply a property that some particles have, and others do not. A given, written into the world at the deepest level we have reached, with no deeper why beneath it yet. And there are real puzzles tangled up in that silence. Here is one that troubled the physicist Richard Feynman his whole life. When you measure how strongly two electrons push apart, how strong the electric force really is, you can boil it down to a single pure number, a number with no units, that sets the strength of all electricity and magnetism in the universe. It comes out to roughly 1/137. Just that. A plain number. And nobody knows why it has that value. It is not predicted by any deeper theory. It is simply measured and put into the equations by hand, and everything electrical depends on it. If it were much different, atoms would not hold together the way they do, chemistry would not work, and you would not be here. Feynman called it one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding. We can weigh it to astonishing precision. We cannot say where it comes from. It is written on the wall, and we cannot read the hand that wrote it. Here is another quiet mystery. Charge comes in exact lumps, always a whole number of electron charges, never a fraction, across the entire universe, in every particle we can freely find. Why should that be? Why is charge so perfectly grainy, so exactly quantized, when nothing obvious forces it to be? There are hints of an answer, deep ideas about the structure of the forces, but nothing settled. And the proton, the positive heart of the atom, carries a charge exactly equal and opposite to the electrons, to a staggering precision, even though a proton is a big, messy thing made of smaller pieces, and an electron seems to be a simple point. Why they should match so perfectly is not fully understood either. These are not small gaps. They sit right underneath the most successful theory in the history of science. We built the entire electrical world, lit the cities, sent the signals, mapped the brain, all without ever quite knowing what the charge doing all of it truly is. And that is a familiar feeling by now, if you have listened to these stories before. It is the same shape every time. We learn to use something long before we learn what it is. We described gravity for centuries without knowing its nature. We wielded electricity, named it, harnessed it, filled the world with it, and at the bottom it stays a little mysterious, a property without an origin, a number without a reason. That is not a failure. It is just the honest edge of how far we have come, and it is a soft place to rest, honestly, because it means the universe still has secrets, still holds a few things back, even in the most ordinary corner of your house, in the wire behind the wall. Now, let the wire go and widen out, because there is something worth noticing about the room you are lying in before we begin the long way home. You think of it as quiet and empty, the dark air between the walls holding nothing much. It is not empty at all. It is full, right now, of electromagnetic fields, crossing it in every direction, passing through you, unfelt. Remember what Maxwell showed us. Light is an electromagnetic wave, and light is only one small band of a vast family, all of them the same kind of rippling field, differing only in how fast they tremble. So consider what is actually streaming through the dark around you. There is the faint warmth coming off your own body, which is infrared light, an electromagnetic glow pouring off your skin this very moment. There is radio from distant towers, passing through the walls and through you as if you were not there, carrying voices and music you cannot hear without a receiver. There is the signal from the phone on the table and the wireless hum of the house, all of it electromagnetic waves, all of it the same stuff as visible light, weaving invisibly through the room. If your eyes could see radio, the night would blaze, and threading through all of it, arriving from the depths of space, is the faint afterglow of the beginning of the universe itself, a whisper of microwaves that has been traveling for nearly 14 billion years and is passing through this room and through you as gently as everything else. You are bathed in fields. You always have been. Every wave of it is the descendant of the same simple thing, a charge, somewhere, jiggling, sending out a ripple in the electromagnetic field, exactly as Hertz first did on purpose in his laboratory, exactly as the amber did in a small way when someone rubbed it thousands of years ago. The whole invisible ocean around you is charge, talking to charge, across the empty dark, in the language of light. And you sit in the middle of it, made of charge yourself, quietly glowing with your own warmth, a small electrical being in a sea of fields. There is one last strange thing to hold before we come home, though, and it is the strangest of all, because it is about the little electron itself, the thing we have been chasing all night, and whether it is even a thing at all. We have been picturing the electron as a tiny ball this whole time, a speck, a grain, small but solid, a little marble of charge. It is a useful picture, and it is wrong in two different ways at once, and both of them are worth carrying into sleep, gently, without needing to resolve them. The first is that the electron has no size. As far as anyone has ever been able to measure, and we have measured very hard, the electron is a point, not a small ball, a true point, with no width at all, no surface, no inside. All of its charge, all of its being, is concentrated at a place with no size. That should trouble you a little if you let it, because a finite amount of charge crammed into no space at all ought to cause all kinds of trouble in the mathematics, and it does. Physicists have wrestled with the infinities that come from a point electron for the better part of a century, and they have learned to work around them with great skill, and they still cannot really say what it means for something real to have no size. The carrier of all electricity may be a place, not a thing, and the second way the little ball is wrong is stranger still. The electron is also a wave, not sometimes one and sometimes the other, but somehow both, in a way that does not fit anything in ordinary life. If you send single electrons, one at a time, at a barrier with two narrow slits in it, each electron does not simply go through one slit like a thrown pebble. It goes through both, as a wave would, and interferes with itself on the far side, building up a striped pattern that only makes sense if each single electron passed through both openings at once and overlapped with itself. Fire them one by one, with long gaps between, and the pattern still builds, as though each lonely electron were quietly a wave spread across both paths. Try to catch it in the act, put a detector at the slits to see which one it really goes through, and the wave behavior vanishes, and it acts like a particle again. The electron is not a little ball, and it is not quite a wave. It is something with no everyday name that behaves like a spread-out wave of possibility until it is measured, and then shows up as a point. That is what electricity is made of, at the very bottom, not tiny marbles, point-like ripples of a field, spread out like waves, that only become definite when the world asks them where they are. So the honest, final answer to what electricity is made of is soft and strange and a little wonderful. It is made of electrons, which are not solid balls, but sizeless points, which are also waves, which are ripples in a field that fills all of space, which barely move even when the current is on, which flow in the direction opposite to the arrow we draw, whose energy travels in the fields around them rather than in the particles, and whose deepest property, charge, we can measure perfectly and cannot explain at all. Every part of the simple picture, the little balls racing down the pipe, has quietly dissolved. What is left is fields and ripples, and a couple of magic numbers we cannot account for, holding up the entire electrical world and holding together the atoms of your body and running the thought you are having about them right now. And that is plenty. That is a lovely thing to not fully understand as you fall asleep. So now, at last, let's come down through all of it, gently, back to the small warm body at the center of the sea of fields. Back home. So let the whole long story settle now, the way you let go of a day, and let the people we met tonight drift off one by one into the dark. The ancient Greek turning a piece of amber in his fingers, watching it lift a thread, with no idea he was holding the root of a word that would name the modern world. William Gilbert, physician to a queen, patiently sorting the amber from the lodestone and coining a new word for it. Stephen Gray, poor and overlooked, sending electricity down a damp thread. Dufay finding the two kinds. Franklin flying something into a storm and guessing the direction of flow, honestly and backward. Galvani and his twitching frogs. Volta stacking metal and brine into the first steady current. You do not have to keep any of their names. Let them go. Ørsted, watching a compass swing beside a wire and hardly believing it. Ampere working out the mathematics in a fever of weeks. Faraday, the bookbinder's boy who could not do the equations and saw the fields anyway, in the curve of iron filings, more clearly than anyone before or since. Maxwell, quiet and devout, writing Faraday's pictures into equations and finding light hiding inside them. Thomson pulling the electron out of a glowing tube. Millikan floating his oil drops. Dirac, staring at his own equation until a mirror twin of the electron fell out of it. They did all the work so the understanding would exist in the world, not so that you would have to carry it. Let their names drift off like everything else. The understanding does not live in your memory tonight. It lives out there, in every wire and every nerve, whether or not you remember a word of it. And let the confusion settle too, gently, because it was never a problem to solve before you could rest. We do not know what charge is. We do not know why it comes in those exact lumps. We cannot explain that magic number, the 1 near 1 over 137, that sets the strength of all of it. We cannot quite say what it means for the electron to be a point with no size, or a wave that goes through 2 doors at once. We built the entire electrical world without answering any of that, and the world runs perfectly well regardless, and so do you. Those open questions are out there in the dark right now, being turned over by people who love them, and not one of them needs anything from you tonight. So let's come down through all of it, slowly, back to the body on the bed. Start with the wide, invisible ocean, the fields filling the room, the radio and the warmth and the ancient faint glow from the beginning of the universe, all of it passing through the dark around you, unfelt. Let it fade into the background where it belongs. Come inward, past the walls with their quiet wires, where the electrons are not racing anywhere but only trembling in place, 60 times a second, going nowhere all night long while the light holds steady. Come in past the still air, to the bed, to the covers, to the warmth held under them, to your own body, lying here, glowing softly with its own heat, which is only light, which is only the same fields, pouring gently off your skin. Let the far things go first. Let the aurora fade, up over the pole, silent and green. Let the sun's wind blow past the earth, unfelt. Let the great cables under the oceans hum on with their messages, far away in the cold, dark water. Let the power lines carry their high voltage across the hills, humming faintly, no concern of yours tonight. Let the storm, if there is one, drift over the house and away. Only charge going home. None of it needs you. Let it all move off to the edges of the dark and grow quiet. Come nearer now. Come to the house, to the wires in its walls, thin rivers of copper you never think about. There is a whole quiet grid out there, reaching back through the streets, to the towers, to some great spinning machine in a power station miles away, a turbine turning magnets past coils, exactly as Faraday found. All of that, so a lamp can glow if you wish it, and all along those wires, the electrons only tremble, back and forth, going nowhere, faithful and still. Let them tremble on without you. Come to the room. Come to the small warm space around the bed. The fields still cross it, the radio and the warmth and the ancient light, but let them thin to a soft background hum. Come to the covers. Come to the weight of them. Come to the warmth held underneath, your own warmth, which is light, pouring off you into the dark. And come, at last, to the body, to you, to the quiet electrical thing lying here in the dark, breathing, and rest there. There is nowhere further in to go. You have come all the way down, from the sun's light in the sky to the small current in your own chest. Feel the bed beneath you. Feel where you are held. Feel the slow rise and fall of your breath. And somewhere in there, steady and soft, feel the beat of your heart, running on the same current as the lightning in the lamp, keeping its rhythm without a single thought from you, as it has every moment of your life. And come all the way in, to the electricity that is you. Because you are not a thing that merely uses electricity. You are made of it and run by it at every level, right down to the bonds that hold you together. Every atom in your body is held in its shape by electrons, arranged and shared, an electrical architecture built over billions of years. Every molecule of you, every strand, every cell wall, is electrons doing the holding. The water in you, the salt, the long folded threads that carry the pattern of you, all of it is kept in form by the same quiet force that lifts a thread toward a piece of rubbed amber. You are, quite literally, an electrical structure, standing and breathing in the dark. And the you that thinks, the you that is listening right now, is electrical too. In your chest, your heart is beating because a small wave of charge is sweeping across it, over and over, steady and faithful, a pulse of electricity you have never once had to think about, that started before you were born and has not stopped since. Feel it there, if you can, that soft, reliable rhythm, running on the same current as the lightning and the lamp. And in your mind, this very thought, these very words settling into you, are a pattern of tiny electrical signals crossing the dark of your brain. 10 billion small cells whispering to each other in pulses of charge. You are a slow, warm electrical storm, gentle and self-aware, thinking, for a little while, about the very thing you are made of. The amber and the thought are the same story. You are where the story arrives. And it is such a quiet thing, this electricity that is you. It makes no sound. It has no weight you can feel. You have carried it every second of your life and never once noticed it running. Every time you moved a hand, a small current ran down your arm to the muscle. Everything you have ever seen became a pulse of charge on its way to your mind. Every feeling, every memory, every dream you are about to have is charge moving in the warm dark of you. You do not have to do anything to keep it going. It simply runs, faithful and unhurried, the way it has since before you can remember, the way it will while you sleep tonight. It asks nothing. It waited in the amber and the storm for thousands of years, and it will keep its quiet current in you all night long, whether you follow it or not. You can simply let it hum and rest. And some of the electrons doing all of this are almost unimaginably old. The very stuff of charge, the particles themselves, have been around since close to the beginning of everything. The electrons in your heartbeat, in your hands, in the thought you are having, were made in the first moments of the universe, nearly 14 billion years ago, and have been drifting and gathering and taking part in things ever since. They are not new. Nothing about you, at the deepest level, is new. You are the latest arrangement of some of the oldest things there are, ancient ripples of charge, briefly gathered into a person, briefly lying in a bed, briefly wondering where they came from. So there is nothing you need to do now, and nothing you need to hold. The electricity will keep running whether or not you attend to it. Your heart will keep its beat without your help. The fields will keep crossing the room. The ancient light will keep raining softly through the dark. The electrons in the walls will keep their patient trembling, and none of it, not one bit of it, asks anything of you tonight. It will all still be here in the morning, doing exactly what it has always done, and so will you, run by the same quiet current, held in the same electrical shape. You do not have to remember any of it. There is no test in the morning, no need to know a Cepheid from a Coulomb, no need to recall who found the electron or which way the current flows. Let the names go. Let the numbers go, the volts and the amps and the magic constant we cannot explain. All of it out of your hands. It was never yours to carry. It was only something to listen to on the way down into sleep. All that is left, the only thing being asked of you now, is to lie here and be what you already are. A small, warm, electrical being made of ancient charge, glowing softly in the dark, held together by the gentlest force there is. So let your breathing slow. Let the fields hum on, far away and all around without you. Let your heart keep its quiet current. Let the whole invisible ocean carry on exactly as it always has, needing no witness, asking no attention. There is nothing to do but rest here, held in your own electrical shape, in a quiet, dark room, at the still center of a sea of light you cannot see. So let the last of it go now. Let the amber go, and the storm, and the eel in the dark river. Let the wires go quiet in the walls. Let the great cable rest on the sea floor. Let the aurora fade over the pole. Let Franklin and Faraday and Maxwell and all the rest drift off into the dark, their work long done. You do not have to hold any of it. Not a name, not a number, not the volts, not the amps, not the little constant nobody can explain. Let it all settle out of your hands. It was only ever something to listen to on the way down. There is nothing to do now. Your heart will keep its current. Your nerves will keep their quiet signals. The fields will keep crossing the room, and none of it needs you awake. It will all carry on, exactly as it always has, whether you follow it or not. So you can let go. You can set the whole bright, humming world down, and simply be the small, warm electrical thing that you are, lying here, breathing, held. The room is dark. The current is steady. The fields are carrying on, everywhere, the way they always have, and you do not have to help them, or understand them, or stay awake for any of it. You only have to lie here and be held. So just rest now. It will all still be here, and so will you. Good night.